We introduced Bi-LR fusion, a bi-directional fusion framework that uses the complementary LiDAR and radar data for improving 3D dynamic object detection. This is a joint work by University of Science and Technology of China, the University of Sydney, IFNITEC, and Shanghai Air Lab. We will first have a 1-minute summary of our method, and the full version will start after this. We introduce a bidirectional fusion framework that uses the complementary LiDAR and radar data for improving 3D dynamic object detection. Unlike existing LiDAR-Radar fusion streams that directly integrate radar features into the LiDAR-centric pipeline, we first make radar features more discriminative by transferring the knowledge from LiDAR data to the radar features, which alleviates the problems with radar data, including the lack of object height measurements and extreme sparsity. With our bidirectional fusion framework, Bi-LR fusion outperforms the earlier streams for detecting dynamic objects on both nuisance and Oxford radar robot car datasets. We know that LiDAR and radar are two complementary sensing approaches in that LiDAR specializes in capturing an object's 3D shape, including depth and height, while radar provides longer detection ranges as well as velocity hints. Though seemingly natural, how to efficiently combine them for improved feature representation is still unclear. There are two main challenges. Firstly, due to the lack of height information, radar points may fall at different locations on an object's bounding box, depending upon the actual height of the object. The improvement by involving radar data is not consistently for objects with different height. For example, taller objects like trunk, bus, and trainer do not enjoy as much performance gain. Secondly, taking the data from the nuisance dataset as an example, the LiDAR sensor produces about 30,000 points, while the radar sensor only captures about 200 points for the same thing. The resulting radar BEV features hardly attains valid local information after being processed by local operators such as convolutional kernels. In this work, we address the two challenges through a method called Bi-LR fusion. Let us see how our method works. In the first step, we use a LiDAR feature stream to encode LiDAR BEV features from LiDAR data, and a radar feature stream to encode radar BEV features. In the second step, we design a LiDAR to radar fusion module composed of a query-based height feature fusion block and a query-based BEV feature fusion block to enhance radar features from LiDAR raw points and LiDAR features. To be more specific, we query and group LiDAR points and LiDAR BEV features that are close to the location of each non-empty grid cell on the radar BEV feature map, respectively. The grouped LiDAR points are aggregated to formulate sealed radar height features, and the grouped LiDAR BEV features are aggregated to produce sealed radar BEV features. Through the two query-based feature fusion blocks, we can transfer the knowledge from LiDAR data to radar features, leading to much enriched radar features. In the third step, we fuse back the enhanced radar features to the LiDAR-centric detection network via R2L fusion module. In the final step, we apply a BEV detection network that uses the features from the R2L fusion module to predict 3D bounding boxes for dynamic objects. Next, let us see how our model performs on the popular nuisance benchmark. Compared with the state-of-art LiDAR-only baseline center point, our method shows 2.7 MAP improvement. Furthermore, we also show the effect of object velocity. Performance improvement is more pronounced for objects with high velocity, which proves that the effectiveness of LiDAR in detecting dynamic objects. Now, let us see a visualization of our model detection output.